this is going to grow. And then there's some predictions that say that the demand could explode, like 5x the demand by 2035, with some reasonable but high demand estimates. So welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
Yeah.
You sound great, man. You think you're good. He says with great confidence.
Yeah, thanks.
You're always just brimming full of confidence, Christopher.
Well, I'm just wondering how you're going to come at me to intro the episode this time, because you usually come in and you're like, hi, Chris.
Here's what I like to do. I like to throw you off your game a little bit, Chris. I like to get the real Chris boys showing up, and I only get that by throwing you off your game a little bit, throwing you off the script.
You might get angry Chris then,
Oh,
you never know.
That's true.
I don't know.
Disturbed Chris, agitated Chris. Chris doesn't get
agitated
angry. Chris gets agitated. Worked up.
Yeah, that's right. He does.
Hey, Chris, this is this episode today. We're talking about the geology of cobalt, which cobalt's not something we cover in most classes. It's not something that a lot of researchers think about. It's kind of what's the phrase I'm looking for? It's something that it's kind of a secondhand consideration, really, cobalt as a mineral.
Okay, I have a question for you then.
Yeah, go ahead.
Well, okay, but cobalt is listed as a critical element.
Yeah.
Why is lithium not listed as a critical element yet, anyway?
Yet.
What's going on with that?
Yes, I think that's a good question. Lithium, I think, might make it onto. There's politics behind what gets onto the critical list and what doesn't a bit, as in all things, I suppose. I think lithium is quite abundant, and the processing is a little bit easier. I think the critical part is like the strategic versus critical part, I think, is an important distinction. And we'll talk about cobalt's one of them. Cobalt, if you read the news, you will have seen articles about cobalt. Maybe not explicitly cobalt, but you will have seen articles about the mining, the repercussions of mining of cobalt, the sourcing of cobalt, which is it's a depressing, I think, kind of state of play, I think, Chris. Like that
Why do you say that? Why do you say it's in the depressing?
We'll get into this a little bit, but we get a huge amount of our cobalt comes from, I would say, mining practices that are both environmentally and socially in the gray at the very least.
Well,
really bad,
at the very
actually,
least. Yeah.
Right.
Yeah. Very volatile areas of the world too.
Extremely volatile. And there's some descriptions of these types of things that are described as modern day slavery. There's a Cobalt Red book that was written recently that attracted a lot of attention to this artisanal mining and really rough socioeconomic conditions. So we're going to talk about all that a little bit. We're going to allude to that, but we're really going to talk about the geology here, Chris, because it is one of these minerals or these elements that is super important for the energy transition. It's on everybody's critical mineral list, and it's a really important one to consider. And in this sort of like societal conversation about, is it better in our backyard? I think cobalt is one that people point to during that conversation.
Yeah, absolutely, Jesse. Before we get into the geology of it, though, the geoscience of cobalt and what we know about, where to find this stuff and how it formed and all that, let's get into the uses. Let's set the stage with that.
Good.
Okay. Why is cobalt important? Why is it listed as a critical element? And we'll talk a little bit about demand, and then we'll get into some of the social issues. And then we're going to end the episode by getting into the weeds with the geology of cobalt. But we're going to be deliberate about, I talked to you about before we started this, Jesse, and I'm holding you to it. I'm going to do my job.
You sat me down and gave me a talking to, Chris.
We did. I did. I sat you down.
There's some big words here in this conversation, and we need to keep it simple.
We need to be deliberate about taking a high level view on this.
Yes.
And so that's going to be our job today, is to boil this down and keep it. It is a very relevant topic. And I want to make sure that comes across and doesn't get lost in all the big words. So that's our job.
That's a great point, Chris. So let's maybe turn to let's talk about the uses first before we turn to any of the images. Cobalt. So
hold on, Jesse. What is your favorite use of cobalt?
I I like the corrosion resistance, the corrosion resistant tools, alloys, steels. A lot of the ones we talk about as critical elements have that as a use case. Mix it in with steel and it makes some really resistant tool. So I like those ones. What about you?
What caught me was the use in airbags.
Oh,
That was
interesting. Okay,
that was a surprising thing for me. It's not the primary gas in an airbag, but it is important because it's a catalyst to ensure that the airbags inflate fast enough and safely.
Yeah. Super interesting.
It's and I actually went down a rabbit hole in this because I found
yeah?
it to be really interesting. I did. So, and here's where I landed, Jesse. Okay. It's complicated but very cool.
Okay.
So
that's the short of it, short and long of it, huh? It's complicated but cool. So how much, out of curiosity, how much cobalt, is in an airbag? I mean, I'm guessing it's a pretty small amount, actually.
It is a tiny amount, but it's a very important gas that's used.
And this is a common theme in the critical minerals list, or the critical elements list of things, is that they don't have to be used in large volumes, in large quantities to be critical. They just have to be really kind of essential and hard to replace, and also have a supply chain that's pretty critical. A lot of those things come to bear here on cobalt when we're talking about it.
It certainly does.
Yeah, a lot of different things. So what is it used in? It's in the electric 18, the elements that kind of we think of are key for an electric transition or an energy transition, used in rechargeable batteries as electrodes. So you think nickel, manganese, cobalt batteries, or nickel, cobalt, aluminum oxide batteries. This is where it kind of gets the future demand cobalt will be essential, and the growth in demand for cobalt is kind of coming from this battery area, I think, of the market. So
is it used as a replacement for anything that maybe we have a harder time getting?
I think probably a really important question is what new battery technologies could you replace it with? So for instance, copper, we've talked about copper and how it's used in electric vehicles. There's I forget the number, 7 times more copper used in an EV than in a gas vehicle. But when it comes down to it, a lot of that could be replaced with aluminum. Aluminum's way cheaper. It is a conductor. It just would not be as good of a conductor. So I'm not sure for cobalt if you can replace it with something in these batteries and just lose a little bit of efficiency. But again, with these batteries, we need these things as efficient as possible. We can't be losing any efficiency in your batteries, right?
No, we cannot, because I just bought more battery tools this week. And
oh yeah, what kind? What did you get?
I got a weed whip.
Oh, nice. Okay.
Because I have a really nice gas powered weed whip. It's a steel, but Jenny cannot start it ever, and she gets frustrated. And so I'm like, you know what? I'm going to sell that. I'm gonna put a good price on it and sell it to somebody that needs it, and then I'm gonna get myself an electric one. Yeah.
Jenny just can't, be relying on you to start the weed whipper.
No.
That's too frustrating for her. It's fun. You're fine with it, but she gets frustrated by that, I'm sure.
Well, yeah, I puff my chest out a little bit as I walk out to start it up.
Strut over there. Sure, honey, I can start that for you.
Yeah.
Look at my bicep while I do it. You flex a little bit.
I'm like, wait a minute, I have to get off my tractor to start this. Then I get irritated. So
bring it to me, honey. Bring it to me on the tractor.
So couple other things, Jesse, about cobalt. It is a super alloy that's used in turbines, or the turbine engines. And another thing is too, that it's, you already mentioned it, it's corrosion resistant, but it's very hard. And also an important property is that it stays magnetized at high temperatures. I don't know. I found that to be an interesting thing, because I guess, I don't know. What about you? Did you think about the Curie point of iron? And I never really thought about it that way before, that different alloys can maybe have, or different metals have different, their own different Curie points, I guess.
Curie. Yeah, that's it. I think I've never thought about it from a pure metal standpoint. And I'm imagining just now, thinking through the use cases of it. Of course, that's going to be useful if it can have an induced magnetic field and stay that way to high temperature. Of course, it's going to be useful. So yeah, this is an element. It's a critical element on almost everybody's list. It is listed as critical. The demand is going to be increasing in the future, at least the rate of GDP growth as we predict, and especially as many countries start to come online and electrify even more, this is going to grow. And then there's some predictions that say the demand could explode, 5x the demand by 2035, with some reasonable but high demand estimates. So we're going to need more of it, either a little bit more or a lot of it more, but we're going to need no more of it in the future. So this is where I think we should probably, Chris, start thinking about where this stuff comes from and just touch on the social issues briefly, because this is in the news. These social issues are very, like, they're, at least for me, in my frontal lobe. Like, these things are things that come up, maybe not daily, but weekly. Things like this come across my desk or come across, what I'm reading in the news. So yeah, Chris, this is this is a mineral element that is going to be important, and demand is going to be increasing, at least at the rate of GDP growth. And so as more countries sort of come online and electrify, cobalt is going to be something we need. That's at a minimum, really. I've seen some of these predictions that are, they're pretty arm wavy, but that predicts something like 5x demand by 2035 in highest but reasonable still demand estimates. So the curve for cobalt, we're going to need more of it. And this is very common. We kind of touched on this earlier. This is very common amongst the critical minerals, critical elements, is that they don't have to be a huge volume of demand. It just is usually future growth of that demand, and these things have to be kind of essential. And in cobalt specifically, there are these societal, environmental issues that are really in the forefront of our mind when we think about cobalt mining in the current state of play in cobalt mining. So I don't know, Chris, what stands out to you about the societal issues at play here when we start speaking about the current state of cobalt mining?
Yeah, well, Jesse, flip to image number 1 a second, and I think that stands out. 65%, as of 2023, 65% of all the world's cobalt production comes out of the Democratic Republic of Congo. There are serious concerns about the, how environmentally friendly the mining process is, and also the human aspect of how the mining is going, are very, very
massive. So yeah, just for the podcast listeners that maybe can't see this image, Chris, this image is a recent image of the amount of cobalt coming from different countries per year. In Congo, the DRC, Kinshasa has 55% of the currently extracted cobalt.
Yeah, I think that this graphic is a little older though, Jesse, because the numbers you and I came across as of 2023, it was 65% coming from Congo.
So it's just growing. And the next biggest one on this graphic is Canada, 6%, right? So, and then China, 6%, Russia, 6%, Zambia, 5%. So it's Congo, Kinshasa, the DRC, and then everything else is kind of, there's no real second place, right? It's number 4, 5, 6. So that's exactly right. Sorry I interrupted you there. I just wanted to paint the visual here for the listener.
No, that's fine. Those are some of the social issues. Another one is that we're really looking hard at seafloor mining, and that has social concerns and issues that go along with it as well. So definitely not cut and dry. Let's go get it. Right. And it has subtleties to it, nuances.
That's right. And we'll come back to this, Chris, but to kind of finish this off by touching on the kind of criticality of cobalt is that the United States imports 75 to 80% of its yearly supply of cobalt. Most of that remaining 20-25% comes from recycled scrap, and almost all, as with many of these critical elements, a lot of the processing. So, you get ore out of the ground, but it has to be processed in order to make it useful into batteries or steels or whatever we're doing. The processing is dominated by China here, as with many of these things. And so there are geopolitical concerns when it comes to that. And so I think, Chris, should we move into the geology here and get into just move into the geoscience here and talk about what cobalt kind of relates to and how it works in the earth at a really, really basic level, and then talk about the deposit types? Is that a good way for staying out of the weeds, or
I think you're right. There's one other thing that I think is really noteworthy about cobalt.
Okay, go.
Is that it's in vitamin B12, and I don't know. That's a
Your biologist father's just shining. She's just smiling right now.
Well, I know.
Got to mention the biology here of cobalt. Absolutely.
But it has this unique ability to form and break these cobalt carbon bonds. It's all in that makes the chemistry of what vitamin B12 does for especially older people. It makes it possible. And so it's I don't know. I think that's another really interesting use for cobalt. I don't think like that's very intuitive.
No,
you go
absolutely
from
not. Oh,
used in airbags to used in vitamin B12.
yeah, exactly. To being kind of bioessential. However, it's also toxic. It can be very toxic when it gets above certain concentrations, obviously, as well, like many of these things. Chris, one last point that I think is really important as we bleed into this geological discussion now of the geology of cobalt is that almost all of the cobalt produced is produced as a byproduct of mining other metals. So what does that mean? It means that you're not going to make a cobalt mine just to get cobalt out. It means you're going to make a copper mine, and there's cobalt in those minerals as well. And so you get the cobalt out as a kind of an extra added benefit. Not necessarily an extra added benefit. It makes the economics of your mine better, more sustainable. You're going to make more profit maybe if there's a bunch of cobalt in it, but it's not the primary thing you're chasing. It's not the reason you're building the mine. That's the current state of play right now. That might be changing in the future.
That's right. What happens is that cobalt is the right size and the right charge it's a very suitable ionic replacement for elements like manganese and magnesium and iron. It just fits within that crystal lattice very nicely. And so it's this again, once again, Jesse, we're back to, this really important chemistry concept, ionic substitution. We see it all the time in plagioclase feldspar and olivines and all these different super important and super abundant minerals back to that basic geochemical, I guess, process of ionic substitution.
That's exactly right, Chris. Is beautifully put. Those are the things. So when we think about where is cobalt going to occur, where are we going to find it? You're going to find it in the same settings that concentrate those elements that you just mentioned there.
Now what does that mean then, Jesse?
Right.
Right. And that,
exactly. What does it mean?
You get the segue award because this leads real nice into our beginning of the geology of cobalt. What kind of rocks, think igneous, this is to the listeners, if you think igneous rocks, what kinds of rocks are rich in magnesium and iron particularly? And we're looking at, really, really mafic stuff.
Dare I say, Chris, ultra mafic.
Yes, right. Dare you say, Jesse? There you go.
yes.
Dare you say?
So things like dunite, which is just pure olivine, basically. Serpentinite, which is just altered olivine. Those have a concentration. On average, there's a lot of scatter in here, but on average, the cobalt concentration of those is about 100, 110 parts per million. As we go, if we think, Chris, we talk a lot about crustal differentiation or distillation here, taking the mantle, the ultramafic mantle, melting it, eventually forming granite. That's a multi-step process. We melt the mantle, ultramafic, 110 part per million cobalt. We melt that, we form mafic melt. Mafic rocks, basalts, gabbros, those have about half the concentration of cobalt, 50 parts per million or so on average. Then if we
But Jesse, here's the thing. Here's a question that comes up, though, is that what's more important? And I don't know, maybe you don't know the answer to this either, but what's more important than the ultramafic rocks have about 110 parts per million. Mafic rocks like basalt have only 47 parts per million, but basalt is so much more abundant at the surface. So what's a more important resource? Is it the ultramafic or just the mafic, just because it's sheer volume?
That's a great question, and we'll get there. How about we'll put a pin in it, Chris, if I could use a bullseye system. Let's put a pin in that real quick and just finish this off, because I think this is an interesting point to make, that cobalt behaves kind of the reverse of things like lithium or neodymium, where every time you melt a rock, it gets enriched in the melt. So you melt basalt, or you melt ultramafic rock in the mantle, you form basalt, there's an enrichment step. There's more neodymium in the basalt than there was in the ultramafic rock. Then you melt that basalt and you form granite, and there's more neodymium in that. And then you distill that granite by fractional crystallization, and you end up with a bunch of neodymium and some pegmatite somewhere. Cobalt's the opposite of that. It likes to stay in the minerals. Think of the relationship between magnesium and iron and cobalt. It likes to do that stuff. It likes to go into minerals that have a lot of magnesium in them. Olivine has a lot of magnesium, and olivine stays behind during melting. So the stuff that's left behind, the restite that we call it restite, the stuff that's left behind after melting
You're just making up words right now. You're just making up words right now.
It likes to rest behind.
Oh my gosh.
It's the cobalt stays behind in these, right? And this is going to lead into our thought process about what are geological processes or geological locations where we would find cobalt ores. So just another couple numbers: granite, 3 parts per million cobalt. So very little in granite. Shales, 1920, there's a huge variation in there. Shales, the weathered products of continents, there's some enrichment in there, but it's much less than mafic rocks. It's 20 parts per million. And so, you're not going to look in a shale for a cobalt deposit, whereas you might look in a shale for a lithium deposit or a tungsten deposit or something. So, Chris, I hope if you're listening to this, you've been thinking about which deposits, what kind of rocks we should be looking in for cobalt deposits. And here is image number 2, which is just showing the major breakdown of cobalt deposit, so of sources of cobalt, the major deposit types. There's really 3, and we're going to work through these 3 here. Where, Chris, do you think we should start in these 3? I'll list the 3 real quick. It's magmatic, Let me list the 3, and then I want to know where you want to start. First one, the largest one, stratiform, sediment-hosted copper cobalt. Very similar to our episode on the geology of copper, same kind of deposit type. The second one is magmatic, nickel, copper, cobalt, PGE deposits, magmatic sulfide deposits. That's about 23%. And the last one is nickel, cobalt, laterite deposits. These are so very different, Chris. I have no idea where to start. Like, which one makes the most sense to kind of start on?
All right. There are two lines of thought here. We can start with the most abundant source for cobalt, which would be the sediment-hosted copper cobalt. But I want to start with the magmatic because this is, we just gave this big prelude about the geology of cobalt, and we talked about how it concentrates more in ultramafic rocks by ionic substitution, but yet that is not the most, that's not our most important source for cobalt. So let's go into the magmatic process, and then let's talk a little bit about why more of it is found in this like sediment hosted copper cobalt.
Okay. Sounds good. Let's do it. So the magmatic, I'm going to skip ahead here, Chris, and just show a photo of what an ore might look like. And this is a really fun mineral. I heard about this mineral. It's called scutterudite. This is a photo of a mineral called scutterudite, which is a cobalt nickel arsenic mineral. That's a weird combination of elements, right? It's a really interesting one. It forms in these magmatic nickel, copper, plus or minus cobalt sulfide deposits. And so these things, we've talked about these a little bit before because they form nickel deposits. This is a major source of nickel deposits. They're actually magmatic rocks. And you look at this thing, and this has some replacement textures to it, but this is a crazy igneous rock. A really weird igneous rock that has this.
It almost looks like a meteor,
Yes, exactly. That's really well put, Chris. And I think that's kind of what we should think about this as, is like, these are metals that are settling out that are being extracted from an ultramafic melt. And that's not a very common thing. We don't get ultramafic melts in the crust very much. We get a lot of basalt going into the crust, but ultramafic melts going into the crust are relatively rare. But if they do get put into the crust, ultramafic magma, then you get minerals precipitated out and they get accumulated down, and cobalt and nickel can go into those early crystallizing phases.
This is basically fractional crystallization that you would get, introduced to in, I would think, most intro geoscience courses at the college level.
I think
you're going to get
right.
into you have this definite order in which minerals precipitate out, bones, reaction series, olivine being one of them. Well, olivine, like you just said, is super rich in magnesium, and cobalt likes to substitute for the magnesium. So it can concentrate then in the olivine minerals.
Yes, that's exactly right.
And then what happens then is these early crystals, if that magma is just right, if it's like thin and runny and there's not a lot of convection in this, then it's allowed to, the crystals get bigger and then they settle down to, and they're essentially removed then and prevented from reacting with the melt any further. So
that's exactly right, Chris. There's a couple bushveld intrusion. There are locations on Earth. They're usually a little bit older. They tend to be older. They're not as common on the modern Earth, but going back into the Archean, the land that I study, we have more ultramafic stuff erupted. The mantle, we think, was hotter back then, so it's easier to melt and produce ultramafic lavas, which we call komatiites. So these are ultramafic magmas that are sitting in the crust, and those can crystallize out some of these kind of weird minerals here. Another famous example that was discovered recently in 1993 is Voisey's Bay, and this is a different example here, kind of a slight variation on that theme. And Chris, Here's a photo of one of the rocks from Foynes Bay. This is, again, a weird rock. I'm going to just list the minerals in here. It's pyrrhotite, a lot of pyrrhotite, 75% pyrrhotite, which is just iron, sulfur, FeS. 12% pentlandite, which is iron, nickel, sulfur. It's got chalcopyrite, copper, iron, sulfur, and magnetite, iron oxide. So that's the mineralogy. In this thing, it's thought that this is a magma, that this was a liquid at some point. And so we're going to talk just really briefly, and let me know if this is too in the weeds, Chris, but these are...
I'm getting there. I'm getting there.
Okay. So those minerals we just listed, many people will not have heard of many of those unless you're hunting around for these types of minerals.
I would think the only two that you just listed would be chalcopyrite and magnetite, would be probably familiar to most people.
Yeah, right.
Pyrrhotite and pentlandite, probably no. No,
Probably
I don't think so.
You're right. But this was a magma. This was a weird liquid, right? And so the idea here is that you start out with this ultramafic magma in the crust, starts to crystallize. You get your typical ultramafic minerals, olivine, things like that. At some point, you get to a point where basically you have oil and water present together, where there's so much metal in this silicate liquid that it becomes unhappy and segregates out. We call that immiscibility. And we can get these really metal-rich magmas, basically, that separate out from the silica-rich magmas because the metal has been driven up in the magma so much. So they can then become immiscible. And then you have a really weird iron-sulfur magma, and then you have a silica oxygen magma that we kind of think of as more normal that we would see. So this iron immiscibility happens, especially in some of these very rare and unique magmatic settings.
All right. Well done,
Chris,
Jesse.
Well,
okay.
I want to bring that back to your core. I want to bring that back to your core thing real quick. Like,
my core thing? What do you mean? What are you talking about?
Well, you alluded to the core. Like, it makes you think, the iron in the core, or meteorites. You're talking about meteorites makes you look like a meteorite.
Yeah. Right on.
So this is similar to the core, right? How the core formed. We probably had this iron separated out from the silicate-rich stuff. And it's interesting that still happens at a smaller scale on Earth, I think. And so when that iron liquid comes out, it just takes all the nickel, copper, cobalt along with it. A lot of the platinum group elements that go along with that. So anyway,
they're essentially siderophiles too, Jesse.
There it is. Yes, they are. Nicely done.
Yep.
Nicely done.
Yep. All right, Jesse. So very, very strange magmas. Don't see them much on modern Earth. So they were pretty old. But what about the Sudbury igneous complex, Jesse? Because I've been to Sudbury and I have some really interesting rocks from there, actually.
Oh, yeah. This was Grand Valley does a trip, right? That goes to...
No. I went on Jenny's dad worked for a company and they owned a piece of property on an island. And so we got to go out there once a year and we'd just take one of these flat skiffs, these flat bottom boats. And the caretaker of the property, he was really, really interested in the fact that I'm a geologist. And so he was like, come on, Chris, let's go. I want to take you some cool places.
Oh, amazing.
And so he took me back into these pothole areas and this really exotic looking rocks. And one of the things that he wanted to show me was this, it was a rock that was loaded with silver and loaded with arsenic.
Really? Okay. Interesting.
Yes.
Wow.
And it was in this Sudbury area.
Yeah.
So very familiar with it. I've been there many, many, many times.
So same kind of thing here. Sudbury is, you know what I'm thinking of? I'm thinking of Bancroft, Ontario. Is that where?
Yeah, you are. You're Bancroft.
Okay.
Yeah.
All right.
Yep.
As I remember, Andrew, our little buddy Andrew, I was super jealous because he went to Grand Valley and he got to go on that Bancroft mineral collecting. It was for a mineralogy class, but it's apparently spectacular mineral collecting location. I've still never been. And you guys have some amazing samples from there.
I do. I have some amazing samples from Bancroft. I have a chunk of fluorite now that's the size of a beach ball.
It's so cool.
Just very, very purple. It's amazing. Just so much there. Yeah, absolutely.
So much there. Okay,
so anyway,
that's what I was getting confused with. Well, that's interesting about the Sudbury igneous complex. This is a meteorite impact structure. 1.85, 1.9 billion years ago, meteorite hit and basically shock decompression melting of a huge...
Punched a hole basically in the crust, yeah.
Punched a hole, and you got to think of when a meteorite hits, compresses this stuff, compresses it like crazy, and then that shock wave passes through and decompresses, and the whole thing melts. So you basically melt the crust, a big, bunch of the crust, and some of the mantle probably upwells too, and you get mantle melting going on. Anyway, you basically have a huge lava lake that sits there and can fractionally crystallize. And so there are layers in the Sudbury complex that are also, as you said, what'd you say? You said copper arsenic. Is that what you said?
Silver
arsenic. Okay.
Actually,
so yeah,
yes.
you get there's a lot of different mineral deposits there that are basically kind of the same thing. These are layered igneous complex cobalt deposits in many cases, but we get this magmatic nickel copper sulfide deposits there too.
Well, Jesse, another thing maybe to mention about this is that, I think that's really such a cool story about the Sudbury complex and how this is related to a meteor impact.
Yeah, we got to do an episode on the Sudbury impact structure because it is a very cool geology.
It just makes me think of the possibilities of this because meteor impacts are like exceedingly difficult especially these older ones to find. You'd think they'd be easy, but they're really not because, you have 1 billion years worth of erosion that's happened, or more in this case, 1.9 billion years. They're really hard to you can't just, it's not like walking up to Winslow, Arizona and seeing the meteor, the Barringer crater, it's nothing like that.
That's true.
Think about how long it took us to find the Chicxulub crater, and that it was just 65 million years ago. It took it was a hard thing to find, right? But if we can do that, then maybe we have, maybe we can find another higher percentage source of cobalt. So
yeah, that's right. And Sudbury's anyway. That's exactly right. So Chris, I think we've covered the igneous version here. The magmatic.
I want to move.
Which one's next?
Yeah. I want to move into the sediment
here again. That's
okay.
Just showing us this magmatic nickel copper sulfide deposit that also has cobalt. About 25% of the global distribution of cobalt deposits. What's next? What do you want to talk about next?
I want to move into the sediment-hosted copper cobalt formation, and this is the big dog. So let's talk about the big dog now, which is this is kind of. It maybe seems off topic, right? Or seems weird because we've spent all this time talking about fractional crystallization in igneous rocks and mafic and ultramafic rocks and so on. Now we're talking about this sedimentary rock that hosts a lot of copper and cobalt. So let's get into this.
So the main thing here is that there's really only one location in the world.
This is the thing,
or one region, I guess, that has this, and it's the Central African Copper Belt. That's this big belt in Central Africa, as the name implies, that is a big copper mining district. And cobalt, this sediment-hosted or stratiform sediment-hosted copper cobalt deposits occur in one part of the Central African Copper Belt. And we're not going to get lost in the weeds here with this, but basically the Congo version of the copper belt and part of the Zambian copper belt both have some cobalt, but the Congo has way more. The copper belt, geological province of the copper belt extending into the Congo, has way more cobalt than the other parts, the Zambian part of the Central African copper belt. Now, link it, Chris, to why. Why? You might be thinking, oh my goodness, this is confusing. Why?
Yes.
I think we should keep it kind of simple here.
I agree. So I'll take it from here for just a second. Okay. All right. But this particular copper belt has many mafic and ultramafic intrusions that goes back to what we just talked about, which may have led to then this accumulation of the cobalt in this stratiform rock.
That's exactly right.
So it's a very niche setting. It's at the surface. So therefore it's easier to get to. And it's I don't know, it's very concentrated here for some reason.
That's right. And so there's a weird juxtaposition here in how these elements behave. Is that we've talked about cobalt, we've talked about copper and other things, and nickel and magnesium. We've talked about those in the context of how they behave in magmas, which when comparing a mineral to a magma, they usually want to be in the minerals. So cobalt wants to go into olivine. It's like magnesium. It wants to be in the mineral phase, right? That's one of the main things here. The other aspect of this is that if we compare magmas to fluids or rocks to fluids, so if we're not talking about a magma, but we're talking about a fluid, like a water-rich thing.
Yeah. Hot, salty water, yep.
Hot, salty water. It changes, and copper and cobalt can be moved by water easier, and sometimes they would like to be in the water phase. So this is how you can get what are called stratiform sediment hosted. So it means that they're like being deposited in layers in the sediment, and they're deposited along some chemical gradient. So basically it's the stuff's being moved around and being concentrated during the movement. And so back to why, as you pointed out, there's more mafic and ultramafic rocks in the Congo portion of the Central African Copper Belt. And that's probably the ultimate source, but the ore now sits in a sediment. The concentration was by fluids moving through the crust that concentrated it in the sediments now. Those things moved around, got picked up in fluids, and then we're going through the sediments, hit some chemical gradient, and got deposited, got dumped out, and made a deposit. So does that make sense, that like difference there? I mean, it's a slight but very important difference, I think. Is that, I don't know, what do you...
No, I get it. I think you did a good job. You painted a good picture. It's the proximity of these mafic intrusions and then the fluids that came later that circulated through and among and around these rocks. You know, think about it just kind of pouring through it along the pore spaces and just circulating through and dissolving certain minerals as it went, right? And then precipitating them later on.
That's exactly right. So I think, Chris, this is also a location, or this is the location that we have a lot of social issues, and artisanal mining is one that comes up. I'll show this image here. This is just an image. There are so many social issues with this. It's a relatively impoverished country that has had a long history of extractive industries that have taken, you know, advantage of the resources in the region. Child labor is pervasive here in the DRC. Here's a photo of some artisanal mining, and some of the books that have been written about this, we mentioned it at the outset, called this modern day slavery. The Cobalt Red is a book that was written recently, and you know, this is not in our realm of expertise here, but it's also important to point out that many of the mining rights are owned by Chinese interests. And so this brings back up the kind of geopolitics of these critical minerals. Is they're complicated, right? They are complicated, and we have to think, you know, this energy transition thing, which I think is an important thing, that is, we're going in that direction. We are going in an electrified, maybe not all EVs, but we are going into an energy transition, and where we source our cobalt from isn't a really important conversation. Like, should we be sourcing this more locally, or where areas where we can do a better job environmentally,
Absolutely.
socially, than is
we talked about this
at the moment.
We talked about this in our diamond episodes. I think we did more than one. And, you know, we had that discussion about, you know, and it's important to both of us actually, is that these things are sourced in an ethical way. And that was something that you took the time to make sure of, for sure.
Yeah.
So,
and I think it's an important thing to consider, right? It's an important thing to actually focus on, and to have we need to have the societal discussion, because it's no small thing to make a new cobalt nickel mine in Minnesota or wherever. Like, that's going to affect places, right? That's going to affect the regions, but it's a conversation we kind of have to have. So, Chris,
we got one more.
Okay.
We got one more. We got to talk about laterites.
Laterites.
Nickel,
Ooh.
Cobalt, laterites. So, Jesse,
next image here.
All right. I don't know. I don't get into laterites in my intro class, just from a time standpoint. You know, you and I, in our CampGeo book, we talked about soils, and we got into all the horizons and so on. Do you get into laterites at all with your intro classes? Do you get into soils extensively or not? I just don't have time.
Yeah, I know. I do, in large part because I have a lot of the civil engineers in the intro level class that I teach. I do get a lot of the engineers, and so I feel like it's something that I definitely have to point out, is the implications of this. So yeah, so that's where I bring it in. I do talk about, and I bring in nickel and cobalt mining as well, because a lot of the nickel that we extract comes from basically leaching with acid, leaching these laterite soils in like Indonesia. And these things, we also, the geological story
let's
here.
Talk. Hold on. Let's go back a second, Jess. Let's back out of there. When you say leaching, you're talking about this acidic water that's kind of just permeating through, almost like a water going through a coffee filter, and it's leaching the nickel out of the soil there and bringing it down to lower parts of the subsurface, right? That's what you're talking about when you talk about leaching.
Yes, what I was referring to is leaching, actually extracting that cobalt. Once it's enriched in there, we've got to get it out, and we're basically they're just flushing acid through the soil that's already enriched, the deposit level. But what you're talking about is a really important thing. How do we get a deposit there in the first place? How do we get a soil to be a cobalt deposit? And it's the same thing as nickel. And we did an episode on the geology of nickel titled "The Devil's Metal," which is a great one.
Yeah.
So basically, it's as you described it perfectly. A coffee filter. Certain elements get weathered out really quickly at the top and get removed from the system completely. Certain elements get kind of moved from the top down into the bottom and get concentrated in the bottom, and then some don't move at all. And copper, nickel, cobalt, these are ones that get moved a little bit down and get concentrated. So they're mostly left behind, but they do get concentrated in certain soil horizons. And so cobalt occurs higher up in the sections than nickel because it has a little bit of different chemistry in these things. And it's more often in the limonite, which is the higher up kind of yellowish stuff in here. Limonite is just a bunch of hydrated iron oxide minerals like goethite and a bunch of other things like that. So
yeah, and
that's
it's often
kind
this
of be
kind
left
of like kind of orangish red, like this rusty kind of color, like the surface of Mars, actually.
Yeah, that's I like that. Yeah. That's nice. Yeah, absolutely. I think, I don't know, Chris, that's a relatively simple one. We've kind of talked about this before. Is there anything more?
Yeah. I think one thing is, basically what is a laterite? This isn't a normal kind of soil. Like you said, it's this kind of reddish brown, rusty looking soil, but where do laterites typically form? Right? I think that's the important part about laterites, right?
Yeah, laterites are there's a bunch of different laterites. Some of them are economic, some of them are not economic, but the laterite is it's an extreme soil horizon, right? It's chemical leaching. There's just so much rain, so many chemical reactions being driven that the soil just gets completely leached out. And I just describe it as a rainforest. I mean, think of
it's weathering on steroids. And where does that happen?
It's super weathering. You're going to have this. Yeah, exactly. Yeah. That's a good way to put it. So that's what a laterite deposit is. And then in certain areas, you will have a nickel cobalt deposit form. So again, let's go back. What do we need to form a nickel cobalt deposit? Well, we need mafic and ultramafic rocks. And so you need a combination of these two factors. You need extreme weathering, which often happens at the tropics, and you need ultramafic rock exposed at the surface. And so in places like Indonesia, where we have all these arc systems, there are slivers of mantle and oceanic crust pushed up onto the surface. Those things get extremely weathered in the laterite, and then boom, we have a nickel cobalt deposit in the soil, in a simple term.
So those are, in a nutshell, the three big areas, the big three where we find cobalt.
Yes.
Concentrated.
What else, Chris? Where do we go from here? Because I think there's one more thing we should probably touch on, I think, just because it's extremely buzzwordy and newsworthy here, which is mining the ocean floor, I would say, very simply. That's a very hot topic right now. And there is cobalt down in these things. And so I'm going to skip ahead here to this image. These are submarine, you'll hear them called different things, iron manganese nodules or iron manganese crusts or cobalt crusts. You'll hear them called different things. This is
I think the most common, Jesse, are the manganese nodules. I think that's what most people are going to be maybe vaguely familiar with, the manganese nodules.
Fair enough. Yeah. Yep. And I think this is probably, we should do our own episode on this, because really interesting science here that we're just going to skim the surface of. But these were originally found a long time ago, 1870s. Were found in kind of dredging expeditions on the seafloor. They're iron manganese dominantly, oxyhydroxides. So iron, manganese, and oxygen, and hydrooxygen, precipitated around a nucleus. So they can be really small or they can be really big, 8 inches across or something like that. And this photo comes from a place that has a lot of them. They can cover like 70%, you can see in this photo, of the seafloor. So they can be loaded all over the seafloor. You need...
Question. Why is this so controversial? This idea of, all right, we got a lot of this on the ocean floor, let's go get it. Why is that a touchy topic for so many?
Well, I think there's a lot of unknowns about there's a lot of known environmental impacts. This really comes down to environmental impacts of mining the seafloor. Like, you're disturbing the seabed. There's all these really crazy creatures and critters. Here's a photo of one. You will disturb. This is actually something you can kind of see in this photo. this lives on a stalk that is anchored in this crust, and it just is kind of sitting there like a sail, catching stuff from the current as it goes by. So obviously rare life forms down in the ocean bottom will be disturbed. There's a lot of unknowns about the environmental impacts of this. And so this is a very active conversation for sure.
That's right. And Jesse, to that point too, startups are trying to look into the technology of, having these essentially rovers going on the ocean floor and picking up these manganese nodules and essentially flipping them over and scanning for biology. And then if it's detected, they just put it right back, and
really
move on.
Interesting. Oh, that's cool. Okay. Yeah. Well, it's a very active space. I didn't know that. That's really cool. That's a totally cool approach here. Chris, the processes here are really complicated. We're depositing this really complicated thing. It is one of the slowest depositional rates known. They are millimeters per million years. Incredibly, that's like angstroms, layers of atoms per year is what we're talking about. Incredibly slow depositional rates. So you basically, they are growing so slowly, you have to be in an area where there's basically no sedimentation happening. So there's no sediment, coming. They won't be near continental shelves because you have sediment flowing off the continental shelf. They won't be in places where you're getting a lot of precipitation. So they're in the deep ocean. Places where these things are common. The famous one is the Clarion-Clipperton zone off the west coast of Central America, in the Cook Islands zone in the South Pacific is another one. But it's a really complicated process. They're manganese minerals, and manganese has this kind of 2+ charge, and so it attracts other 2+ elements like cobalt, nickel, manganese, copper.
That's right.
Cobalt's
That's right.
in there, right? So stay tuned and pay attention. And when you read the news and you hear about mining the seafloor, think, cobalt. That's one of the things we're after, or people are after, when they're thinking about mining the seafloor. And there's a lot to be unpacked with that one.
Yeah, you're right. I mean, that's I think a really good point, Jesse, is when you think about manganese nodules, now you also need to think about cobalt.
Yeah.
A critical element.
And Chris, it's for me, this episode's Geology Cobalt, it's a real live wire, this Geology Cobalt one. There's a lot to be discussed that's certainly outside of, my realm of expertise, but we all get to have opinions about it, and it's something that as a society we should be discussing, because there are trade-offs when it comes to this stuff. And it is a critical element that has a lot of environmental and social implications for the extraction of it. So I hope it wasn't a depressing episode. It's interesting geology. At the very least.
It is.
Yeah?
Absolutely.
What's your favorite deposit?
My favorite way that it forms, you think?
Yeah. Or
is that what you're asking?
One that we talked about.
What color do you think of when you think of cobalt?
Ooh, steel blue.
Mm-hmm.
What do you think of?
Deep blue.
Deep blue.
Yes.
Yeah. Is that what you think of?
Yeah, that's what I think of.
Yeah.
Yep.
Okay.
Yeah. Let's see. So anyway, what's the question? What did you ask me?
Got lost already.
I did.
I asked you, what's your favorite deposit type?
I guess, I don't know. I would go with the magmatic formation for sure.
Yeah, you're a magma guy. Me too. They're cool. These weird iron sulfide magma things, they're very cool. I like thinking about those.
Yeah.
They're crazy.
But I do think of these, the stratiform copper cobalt formations in the Congo. I would like to learn more about that. I think that could be super interesting.
Well, I think we should do the Central African Copper Belt is just a massive place for exploration for copper, cobalt, all sorts of stuff. So, we could easily put together a couple episodes on that. I think that would be really interesting to learn about and discuss more for sure.
Oh, let's get sidetracked once again, Jesse. Let's do that. Okay.
We got too much stuff going on right now. Too many projects. What are we working on? We're working on
every time I talk to you, you're like Jenny. Every time I talk to you, I get new tasks. Like,
get more
hey,
work.
Chris, do this, and I do.
Chris,
I don't appreciate it.
About the Central African Copper Belt.
Yeah.
Put a script on it, man. Come on, find a bunch of images. Get going on it. What are you doing with your life?
That's
anyways?
the thing. You're always on me about that. You're like, Chris, good script, but man, you got to put images in here. And I'm like, dang, I'm sick of it. I need to walk away from this for a little bit. It's been too much time.
This is a great little image of this little thing sitting on a stalk, just catching food, hanging out in the breeze down at the ocean bottom.
Yeah, very nice.
All right.
Yeah.
Hey, that's a wrap. You can follow us on all social medias. We are at Planet Geocast. If you're on YouTube or Spotify, leave us a comment. Give us a follow. We always appreciate that. There's a contact us link on our website, planetgeocast.com. You can reach out to us. We love hearing from you. And also download our CampGeo mobile app, first link in the show notes. There you can get access to a whole bunch of visual podcast series, including a new one on the Long Valley caldera. So check that out. First link in your show notes.
Cheers.
Peace.